All right. So if you remember, we showed that these P operators composed after each other are the P operator again. So this just gives Kn. But we skipped a step in the proof. We argued via the triangulation, but we didn't prove it explicitly via string diagrams, and this is what we're going to do today. As a reminder, what do we have to work with? We have the Frobenius identities over there, and we have a braiding. And to use the braiding, I'll just write out how it works. So the braiding is a natural isomorphism. So isomorphism, it has an inverse. This is how we write braiding. The inverse would be this, and that it is the inverse we see via this identity. And also it is natural. That means if we have something like this, and we have a morphism on this, we can pull the morphism through. So this is the same as this. In general, we can think of these strands just like shoelaces being laid on top of each other, if this helps. All right. So where did we stop? What was left to do was to show that this thing is the same as just one of these. Okay? So let's try doing this. How do we start? We just remember what we can use. We can use the braiding, and we can use these identities. For example, we have this here, which looks like this, and we can swap this around to get this in the middle. Now we have to connect the rest of the picture to it. So we have these strands, and then it continues like here. And at the top as well. All right, and I can mark what we did by doing this, so we can remember. All right, next step. Maybe we can use the braiding now. So the braiding is natural. We can pull morphisms through it. This is a morphism, this too. We can just pull it through the braiding if we want to. So let's do that. Look at this. Pull it through. So, do these steps make sense? Who understood these steps so far? Okay, Okay, perfect. Any questions? Wonderful. Let's continue. So now we see down here, badly drawn, but still, we have something we can recognize. This is the co-multiplication, and we can use the associativity law. So we get this. And this at the bottom. And then it continues into this rest. So we switched it here. Everyone still on board? Perfect. All right. That looks okay. Maybe we can do a similar thing like we did here on the bottom, pulling this through and using the associativity law on the top, because it's kind of symmetric. So let's pull this through again. Get this. One of these goes like this. The other one. So, very similar to here. Same thing, we use the naturality of the braiding. And now we can use the associativity of the multiplication. Alright. So this looks a bit weird. Maybe we redraw part of this a little bit. Alright. Mark what we did. And now we can see we have a braiding here, then we have this line which goes over everything, and we have the inverse braiding here. Since we can pull everything that's a morphism through a braiding, so the braiding itself we can pull through too. We can pull one of them to the side of the other one, and then let them eliminate each other. So first we want to do something like this. this make sense to everyone? Any questions? Why this works? No? Perfect. Wonderful. Okay, and now, oh, I think I drew something wrong. Why not? This should be. Seems to be correct. Yeah? Alright, so this should annihilate. I'm not quite
I got to this stage, but I thought we need to use the fact that we have this trivial
that it's symmetric,
gradient,
you mean?
and in fact, more than that is true, but 1 over 1 under also is.
Yes, in this case, because we are in vects, so that's why this works too, right?
Yeah.
So what's being said here is that this is also this in a symmetric case, but only in the symmetric case. So when the braiding is symmetric, this works too. So for now, let's do this.
In that case, oh, okay. No, I was thinking push the. No, never mind. You're about to do it. Push the node, the right node up through the.
This one?
Yes, up to the other through the braid.
Ah, yes, we can do that. We can do that already. You're right, but also we can let these annihilate and then do it afterwards. All right. Let's do it step by step so everyone can see what you mean. So first we let these annihilate, and then we have left. This. And now we do what you already said. So let's see. And we pull this node through, again because of the naturality of the braiding. Do we get? So we pick this up and pull it under the other strand, and now you might see already one more step and we are done, because now we can use this nice relation of our Frobenius algebra. And get to this. And now we're done, because this is exactly what we wanted. This is one of these loop thingies. Are there any questions about this?
Just to comment that the relation you used was not given on the lecture. The middle part was not there, but
yes,
it can be derived.
Yes, exactly.
Kind of adding the co-unit and then remove.
Yes. So you only need this and this to be equal.
That was given. Yes. I mean, that can be derived the middle part from.
That's right. Yeah. For brevity, we can use this. Any questions left? On string diagrams in general, maybe?
So that last.
Sorry? Yeah.
So you mentioned that only in the symmetric case when they are intertwined, like this. But also I would naively think that when we are in vec, since the vector spaces are the same, take two lines and flip them
Yes, in vect the braiding is symmetric. You had a question?
Like it's a separate assumption with respect to all the other inputs that.
This one?
Yes.
So, right, so this is the case for symmetric braidings, and this is the case for all braidings. Since we are in using vect, this is a symmetric braiding, we can do this.
What is written on the left board, these are properties of the algebra. What is written on the right board, these are properties for the whole category in which we work. It's not specific to the choice of algebra, it's always the case.
More questions? All right, we can open it up to a general Q&A about the lecture. So if there are any questions not about only string diagrams, but also about what Nils talked about today or the last few days, now's the time.
Are there any questions? Do you want to speak up, or should I come closer?
Oh no, sorry. So I got a bit lost towards the end when we introduced the N in our category DZ. Should I think of this as some auxiliary category that's unrelated to both board and the category C?
Oh, I would not call it auxiliary. The question is how to think of this N category DZ and whether it might be auxiliary or how it relates to this category, to this category and this category. Is that the question?
Yeah.
So the higher category DZ is something that we can attach to the defect TQFT. So the defect TQFT is everything I want to study when I want to study the defect TQFT. But we can extract part of what the defect TQFT knows in the form of this higher category. So just giving you that higher category is not enough in order to tell you everything about the defect TQFT, but it tells us what the defect TQFT does locally in a ball, in an n-dimensional ball. That's pretty much precisely what it is. Mathematically, you can also think of it as an invariant associated to this functor, but physically, it's what the defect TQFT does to the ball, but it doesn't tell us how to glue balls or pieces of Rn globally into what it does globally. So there's more information in the defect TQFT, but it has a lot of information in this higher category. It's precisely the information about all the bulk theories associated to the defect TQFT. These are the objects. All the codimension whatever topological defects. These are the 1 morphisms, 2 morphisms, up to n morphisms. All the ways they can be fused. And that's it when it's just the category, but there's more structure. Pivotal, so I don't know what a pivotal 3 category is or pivotal 4 category, but we know what a pivotal 2 category is, and what I mean by this is that all the morphisms have adjoints, and the adjoints behave well with one another. And in dimension 1, 2, well, maybe I guess I know what it means in dimension 3. In 1, 2, 3, we know what it is. And does that answer the question?
Yeah. So is it related to the order?
Not yet. But thanks for the question. This has nothing to do with orbifold data directly. So if you have an n-dimensional defect TQFT, then you might want to talk about certain aspects of it, namely the local aspects of it, in terms of something more or less purely algebraic, and that's the higher category. So this higher category tells you what are all the bulk theories, what are all the topological defects, how do they fuse, what are the junctions, meaning what are the orientation reversals for topological defects. That's that. And then you can ask, well, what are orbifold data? How can we gauge symmetries in this defect TQFT? And then you can wonder, how can we express this in terms of this higher category? Or can we even? Or do we need something that is more global than local? But the answer is no, this is good enough. You can reformulate what it means to be an orbifold datum for the whole defect TQFT in terms of something that is entirely algebraic in this higher category. So, for example, if n is equal to 1, then it turns out that dz is simply finite dimensional vector spaces and linear maps between finite dimensional vector spaces. And then you can ask, what are all the condensable symmetries in that theory? And they are just projectors to subvector spaces, idempotents. That's not very interesting. Then you can consider the two-dimensional case and ask, what are all the condensable symmetries or the gaugeable symmetries for two-dimensional topological theories. And then you find that they are delta-separable symmetric Frobenius algebras in this higher category. If this higher category happens to be the delooping of vect, so B vect, meaning the two category with precisely one object, one morphisms are finite dimensional vector spaces and two morphisms are linear maps, then the whole construction tells you it's delta-separable symmetric Frobenius algebras as objects, and bimodules as one morphisms and bimodule maps as two morphisms. And this goes on in dimension 3. One gets something, if one starts with a trivial theory, where you have spherical fusion categories objects, bimodule categories with traces as one morphisms, bimodule functors that are compatible with them as two morphisms, and appropriate natural transformations as three morphisms. Though, and that's a point that I wanted to make, but didn't manage to, there is no need to talk about fusion categories and bimodule categories and these somewhat higher categorical things, unless you want to. The way we set up what the trivial three-dimensional TQFT is, we only ever had to talk about ordinary algebras over a field and bimodules over these algebras. So there's a way that is equivalent to describe all the defects in this 3D Setzer model that only talks about stuff inside vect, only vect, namely algebras and so on. And then there's a version of the so-called Eilenberg-Watts theorem that lets you translate between the fusion category language and the Frobenius algebra language. You?
I've heard this statement about TFT, right? If the object in the target category is fully realizable, the TFT is determined by where the building blocks descend to. So does this also happen for defect TFT?
The question is, or the comment is that there are fully extended TQFTs, and if you have a fully dualizable object in a symmetric monoidal N category, you can build a framed, fully extended TQFT with that target. What is the relationship to defect TQFTs? I think there's at least 3 perspectives I want to give on that. So one is, how do you decide which higher target category to choose when you consider extended TQFTs? And in practice, it appears that, well, you ask what are the topological defects in all the bulk theories you want to consider, and can you then construct at least a non-extended defect TQFT like this, with values in vect or S vect or something? Aha, good. And then you construct the associated higher category, and then you realize, well, but unfortunately this is only an N category with adjoints for morphisms, but we never said that this is a monoidal N category, or even a symmetric monoidal category. So a priori, you cannot immediately ask the question, what is the fully extended TQFT? But in all the examples I know, it's either known or it's known that there's lots of evidence that there is a symmetric monoidal structure on these higher categories, and then this is the correct thing to do. This is true for twisted signal models, for Landau-Ginzburg models, for state sum models, in all the dimensions that are well understood. And there are basically no other TQFTs that I know of. So this is a good source of target categories for fully extended TQFTs. Or it's a good way to think about them. And if you think about them like that, then you're much less surprised or not surprised at all when when you notice that a non-extended TQFT cannot be extended to an extended TQFT with values in higher vector spaces. Higher vector spaces are very special. But if you choose to consider a richer target category, like those associated to twisted signal models, then it might work, and it's known to work for twisted signal models. So that's one part of the answer. Then the other answer is, well, maybe the question is, what exactly does the question mean? So how do you want to marry defects with fully extended TQFTs? And so one way how they connect is what I just discussed. And another way how they connect is that, well, but now we just know what the bulk theories are. Fully dualizable objects allow us to construct bulk theories, fully extended bulk theories. But what are the defects? Well, two comments here. On the one hand, fully extended, fully dualizable objects in the symmetric monoidal N category give precisely framed fully extended TQFTs. I can see reasons why framings can be relevant in condensed matter physics, but in more high energy related QFT, one needs extra structure on space-time, like an orientation or spin or some G-bundle. And then you ask, what does it mean? How do you construct, what else do you need but the fully dualizable object in order to construct, say, a spin TQFT? And there the cobordism hypothesis says that you take the fully dualizable object, and on top of that you need the structure. So you need more than just that piece of data, but other pieces of data. The structure of a homotopy fixed point of the action of the relevant group for the tangential structure. So for spin, it's the spin group. For orientation, it's the SON group, and so on. And figuring out what this is in even in low dimension is not worked out, but in dimension 2 for a handful of tangential structures, I think. Framings, orientations, spin, maybe O2, right now, there's one other that I don't remember right now, but really roughly a handful. And in higher dimensions, it's really not known. Okay, but imagine we work in very low dimension where we know how to do it, or we believe that the cobordism hypothesis is true. What does it say about the defects? And what it says about the defects is that, so choose a stable tangential structure G, like SON or spin N, orientation spin, and then ask what are all the defects in a fully extended TQFT. Again, the bulk theory is given by a homotopy fixed point structure of the G action on the fully dualizable object. But it's, let's say, the GN action, the SON action. In one dimension lower, if we stick to oriented things, then there's an SON-1 action on codimension 1 things. So what's a codimension 1 defect between two oriented fully extended TQFTs? Well, it's a one morphism in the target category that comes with a homotopy fixed point structure of the SON-1 action, and so on and so on. I don't know that this is proven, but this is how I read section 3.4.3 in Louis' paper. But then the very nice thing, and I fear that I don't have a good picture for that, but let's see whether Yeah, like here, for example. So then what the cobordism hypothesis really says is, oh, you want to construct correlators, say, for lots of field and defect configurations in space-time. So imagine this is space-time, and imagine it's the dimension that you like. And then you have this picture, this actual graphical representation of, in this case, this defect pair of pants. And then how do you compute the correlator, or more generally, this linear map from this state space to that state space? How does it go? Well, if you have a defect TQFT, it will tell you how to do it. But if it's a fully extended defect TQFT, then you look at this picture and you don't need to think about the functor itself. You just apply the cobordism hypothesis. And the cobordism hypothesis says this picture is the formula in the sense that there exists a graphical calculus, in this case in dimension 2, where everything is an expression. So for example, this line here is an evaluation 1 morphism from the object U1 composed with the dual of U1 on the other side to the unit object. And this thing here is an evaluation 2 morphism between this evaluation 1 morphism and its adjoint here, and so on and so on. So this, I was very happy when I realized that this is what the cobordism hypothesis with singularities or with defects says. It says that there should be a good graphical calculus in dimension n, so that if you have a representation as an actual higher dimensional graphical diagram for your space-time with defects, then simply read off what it is. Of course, I really can do this only in dimension 1 and 2, because that otherwise it becomes too hard. But one can try and look at movies and movie frames of such things, and then this is what it says. Thanks. Maybe I said 2 or 3, so the first was 1.5.
Okay, thanks.
Let's see whether I don't think I have more.
That's fine. Thank you.
Sorry.
Thanks.
Can you sketch out how the state operator correspondence works on defect Hilbert spaces?
Half the time I forget, and then I need to scratch my head and see whether I can remember.
Or maybe like we could say 2D and with a C2.
Yeah, right. Let's see what I remember while moving the board. Maybe while I pick up the piece of chalk.
Maybe I could like tell you where I'm coming from.
Yes,
So, like,
I remember, but do tell me.
Like, so you had a circle, and in CFT, okay, you could bring out a disk and maybe put some load operators on that disk. Here, obviously, if you take out the disk, that's the unit operator in the Frobenius algebra for 2D, so that's boring. But say you had a circle with 2 point defects separating 2 phases, two theories. Can you still bring that out into a disk and maybe whatever junction you have? Does that, like, my question is, would that label all the states? Because I think that's what it would mean by state operator correspondence.
Oh, now I'm really confused. So let's see what you're saying. So I think you're talking about a closed TQFT, right?
Yeah. I just want like the disk to generate states on a circle.
I think that's not enough. Let's do this. Maybe vect. And then in particular, S1 is sent to Z of S1, call it V as before. And now one question is, how do you find all the elements in that vector space just from the TQFT? Well, the TQFT tells you it's the vector space, full stop. But I think you're asking the question, can I obtain some elements in that vector space as the images of bordisms over here?
Yes.
That is not always the case. But let's see what might happen. So, for example, here we can have the empty set. That's sent to Z of the empty set, and now it's vect. That's just C, right? And then we asked what kind of maps do we have from here to here, and then we get maps from here to here, but a linear map from C to V would send the number 1 to some vector over here, and we ask whether we can get all the vectors little v in here from some bordism here.
Yeah, although I should clarify, like, I understand this, because obviously if there was an operator, that'd be like a puncture on the disk, I guess, which would then just be a cylinder from S1 to S1.
Yeah, but maybe we can effectively construct such an operator. Let's see.
I think he's more asking about D0 completion, so with defects in principle.
With defects?
Yeah, thank you, yes, basically. Because I appreciate what you're doing, but yes, I want a disk with defects, and I'm asking basically.
Oh, I see. Thanks for the clarification. Is it okay if I go on about this for a little bit, because there's more than 3 people in the room? So you were talking about the disk like this, which I think of as the cup from 0 circles to 1 circle, and well, as you say, this is sent to the unit over here. So it's the unit of the underlying commutative for Venus algebra. But you can also take, well, it's the same thing, it's a cup like that, but maybe the cup has a handle, or maybe it has 2 handles, or it has any number of handles, or maybe it's a cup with a little sphere floating around in the background, or a few more of those. These are all, so you take as many handles as you like, and then all kinds of closed surfaces with handles. These are all the morphisms from empty set to circle. And then you can ask, if you look at the images under the functor of all of these, I think of them as socks with holes and ghost donuts that float around. Do you get all the elements in the vector space? And no, in general you don't. I think during one of the lectures I briefly mentioned an example where this doesn't work in a semi-simple case already. But if you get all the elements of all the state spaces, then one says that the TQ of TZ is non-degenerate. We discussed this last week, right? This is, for example, true of Bosanski-Witten, of Reshetik-Toraev models. That's very nice. And since lots of people exclusively think about Reshetik-Toraev models, one might get the impression that's always the case. But it's not always the case. Okay, but now you were asking about D0 completion, as Aaron said. Do you want to comment on the previous thing?
It's true for Reshetik-Toraev models with defects, right? So with embedded ribbon graphs.
Oh, right. Yes, thank you. Thank you. But I still don't precisely understand the question. Am I supposed to explain what D0 completion is?
No. I guess my question is just, if you take a circle, put a disk behind it, decorate that circle and the disk with lines separating D0s, can you label the states with like a junction at the bottom of the disk, connecting the lines? I don't know if that, hopefully that picture makes sense.
I don't follow, sorry, can you? I
mean, it's fine because I can discuss later if you want, but like, I'm literally saying line comes down, meets at a point.
I think
you label that with a morphism.
Say if this is what you mean. So, like, do you have a color? Yes. Decorating like this.
Yes. Yes, and then you label that morphism phi or something, and I'm basically asking if saying what those phi's are is maybe not generates everything, but if they're good states, like, are those good states?
Yeah, I agree. In general, it won't generate everything. But these are special elements in the vector space associated to a circle with 2 such defects.
Yeah, I'm happy. Thank you.
I'm so sorry.
No. If you do this completion procedure, right? So where you make the state space as a dot as big as it can send to B, then by definition, that generates everything.
Yeah, that's what's
I'm unsure how interesting I find this, so I ask for more questions. If there are no more questions, then I'll explain in more detail what Ingrid just said. Thank you.
Is there a Hamiltonian in all of this somewhere?
Yes. Here it is. In if I remember correctly, over here in Caroline's lecture, there was the A and B type thing in the Levin-Wen model, right? And that's another way of writing that. So, but let me add more context. If you start with the trivial defect TQFT in dimension 2+1, and then find an orbifold datum that comes from a spherical fusion category, then you do the thing that I said 15 times. Take your Bordesen, choose a triangulation, put your data, the orbifold data, on the Poincaré dual, evaluate with that, and where necessary, compute the image of some idempotent. Lorenz explained that in dimension 1+1, it really is an idempotent. And similarly, one can prove that these things, where you choose in 2+1 a closed surface E, and then consider it's a cylinder with some triangulation tau here and the same triangulation tau upstairs. This will then be an idempotent. And if you write it out, as Vincentas, Ingo, and Thomas did in their paper 2 years ago, then you recover the commuting projectors of the Levin-Wen model. And more generally, in any theory, if you knew another 3D TQFT, which is not trivial and not trichetic in derive, and then you would do the same thing, you would still obtain linear maps which square to themselves. And then you can wonder, can you describe this as a Hamiltonian whose ground states are the ones that you're interested in? But it happens to be like this. So I don't see directly that obviously this must be a Hamiltonian. I think that's an a posteriori interpretation.
I guess I'm trying to like see where the bridge between this and like kind of more the language I understand is. So like, can you like calculate the energy spectrum using this formalism? Is there any like what calculations can you do that would correspond to something in quantum field theory or a lattice model?
So with one of the few hats that I have is the TQFT hat. If I put that on, then I can calculate nothing but at the ground states. So the TQFT only knows about the ground states. This construction goes through a neighborhood that is a bit more interesting than the ground states, but the actual output of the construction is the TQFT.
I can compute the spectrum of the commuting projector Hamiltonian. What about this 0, 1, 2, 3, right?
Yeah, so here's the Hamiltonian, and then you can compute the spectrum, but it's not a TQFT thing to do that. Yes?
So suppose you have a spherical fusion category such as Fibonacci, and I would think that once you have the fusion rules, you have everything you need to know.
I disagree. I think it's here. We need the fusion rules, but we also need the pivotal structure. So we need the quantum dimensions. And the braiding as well.
And what's the interpretation of these quantum dimensions? How should I think about them?
If you think of the objects in the Fibonacci category as the labels for anyons, then the quantum dimensions are they correspond to little loops of these anyons. So a pair of anyons, anyon, anti-anyon is created, and then they annihilate again.
Thanks.
Does the braiding really matter for you because of how you're producing the Green self-center? So get the braiding and its opposite, and those produce the same output. At least in the Levin-Wen model, right?
Right. So for the state sum model, the braiding, you're just right. So I thought, oh, that's also full stop. You're right. Thank you. The braiding doesn't matter. We're already 3 minutes over time. I'm happy to continue for a little bit, but I'm also.
I mean, if anyone wants to leave, I guess they can.
Yeah, leave.
I was just curious about the question that was raised about anomalies, where there was the slide where we basically want the F symbol condition to hold, and if it's violated, that we could say that there's an anomaly.
Like this?
Yeah, yeah. I mean, just even in the 1+1 case. Yeah,
Like
exactly that.
Here?
Yeah. So, and for group, if we have if fusion rules are described by a group, then we know that the anomalies, so the possible violations of the F symbol, are described by the third cohomology group. So, and I was wondering if for more, for non-invertible fusions, if there could be some mathematical classification or some structure on the possible anomalies of them, or not?
I try to make 2 comments here. So the first one is a repetition of what I said on Tuesday, I think, or was it today, that these are, I claim, the precisely the conditions in order to be able to gauge the symmetry A, and every non-identity is an obstruction. There are no other potential obstructions than these equations not being satisfied. But I think you're asking for a general higher categorical obstruction theory that would specialize to the classification of obstructions via group cohomology in the case of Dijkgraaf-Witten models. Is that true?
Yeah, I mean, if we consider group symmetries in 1+1D, then the obstructions to gauge in it are classified by the third cohomology group. And
yes.
So these possible precocycles have an algebraic structure that they form a group, etc.
Yes.
I was wondering if we have some other fusion rules, for example, for the Ising fusion rules, we can have two inequivalent F symbols. But is there, and so we have the Ising plus and Ising minus categories. Is there some structure that related these 2 inequivalent F symbols?
No, I'm not sure whether I understand the question. So at first I thought the question is there a good mathematical cohomology-like theory for, and the answer is no, not that I know of. I would like to construct it or find it, but it's not done. Full stop. It probably helps to have a higher category that describes the relations of all orbifold data. This is this orbifold completion that we understand in dimension 1, 2, and 3. And so I guess it should be some cohomology theory internal to this higher category dz. But exactly how it works out and exactly how it would recover the case of Dijkgraaf-Witten models, I just don't know. Another comment I wanted to make, if this addresses what you wanted so far sufficiently, was the discussion that we had earlier, where with the help of Ingo, we realized that in the case where we have a group action in dimension 1+1, then this already gives us delta separable, symmetric Frobenius algebras, and this only imposes delta separability. But this is not an extra condition, because a way to think about it is that if you start with a non-topological theory, and you have a group action, and then you construct defects, but they might not be topological. So meaning topological is that in this little circle here, this should add up to the neutral element or something like this. So this is a condition. This is built in here because I start from topological defects. I don't allow myself to work with non-topological defects. But if you start with QFTs and you have lots of defects, then this is a condition that ensures that it's really topological. And that seems to be the case also in higher dimension, that the n+1 partner move has something to do with that. Other questions, comments?
Seems to me like the orbifold construction would work all right for just normal QFTs. So do people use this construction on regular QFTs for topological lines? Like, does this have to be on a TQFT?
Yeah, like Ingo pointed out in the morning, the whole thing also works if you consider QFTs and topological defects between them. So all that is really necessary is to be able to move around the topological defects and have some interpretation of what's going on in the bulk. If you're sufficiently happy with what's going on in the bulk and your understanding and your description of that, then all the stuff which is just the defects, codimension 1 and higher, then it works just as much. Then there's the question, when one does such work actually refer to papers on TQFTs, and when does one just do it? But I think a lot of the constructions can be phrased in this way, or in a way that is very close to this. Yes, if it's oriented. So this is, I think this is a fairly big technical issue, because often it's not. One does not always pay a lot of attention what the correct tangential structure is in physics, because tangential structure is very complicated. But on the other hand, well, that's one reason. But on the other hand, as physicists who want to understand what the electron is, which in the standard model of particle physics is something that transforms in a spinor representation on a spin space-time, and maybe it's not just flat space-time. So this is relevant. So that's one reason to study spin. But it's really complicated, at least if one works in the fully extended TQFT setting, as we just discussed. And quite generally, it's not worked out in a lot of detail how it works for other tangential structures.
I actually just mean to say, in particular, when you orbifolded, one thing you constructed was the Hilbert space, and it required a cylinder. Obviously, in a normal QFT, the length of that cylinder matters. And so that's kind of, like, I'm curious if the orbifold construction can healthily generalize given possible issues like this. Because now you have geometry dependence.
Yeah, maybe I should think more carefully about this, but I think one could then just say, well, in the full QFT, there's the actual geometric parts of the Bordisms where you have real, actual time evolution of spatial slices, and then you have the purely topological thing that could happen instantaneously or not. It's just topological, and then you can zoom in, into which is just a slice, and then you have all these topological defects hidden.
Epsilon size, then put your
yes, something like this.
Okay.
But this reminded me of something else I wanted to say. Oh, maybe one other thing that I used to like a lot. So I tried to do string theory when I was younger, and people in string theory back then, they would consider orbifolds of group actions, and then they wanted to understand d-branes in the orbifolded theory, where instead of a sigma model with target something, you divide it by the group action, and then it wasn't a manifold anymore, but some stack, and it was called an orbifold, and how to deal with that. And then they would add twisted sectors. What does it mean? I didn't understand it. So it seemed like an art, like a mystery. If you add these twisted sectors, then you get a consistent theory. I'm sure many people in the room can understand this properly and explain this properly, but I didn't understand it in general. But in the context where we have a group action that we can describe by orbifold data in the way that we considered, and then just a closed sector, and using the stuff with the bimodules and the bimodule maps, that's the natural thing to do, to just ask, well, in the closed sector, what is the bulk space of states in the orbifolded theory? Well, you just take the invisible line defect and ask, what can you put on the invisible line defect? But if the theory is the orbifold by A, then the invisible line defect is just the algebra A viewed as a module over itself. So what you're supposed to do then is to consider endomorphisms of the algebra A, which are also AA bimodule maps. And just something that you can compute if A is a delta set symmetric Frobenius algebra. And then you see it's literally a direct sum of Hom from the identity object into the object associated to a group element, and then you sum over all groups that satisfy some properties. So the twisted sectors, they just come out of this. And I like that very much. And this lifts also to higher dimensions. So this is, I say this because I like it and because it seems to work with what you asked, how is this relevant for non-topological stuff? Because you can look at group symmetries on non-topological QFTs like sigma models before twisting, and this still works. Was that the last question? Good. Thanks for your interest.